Hello, we are here to talk about parallelization in our HPC kitchen metaphor. So let's start with an example. So I have a stove here with 4 burners. Am I able to cook an 8-minute pasta in 2 minutes? Well, it's kind of obviously no, because that's just not how pasta cooking works. There's a certain amount of work that has to be done in a certain order. And yeah, it's sort of intrinsic to the recipe, the algorithm. Can it be done this way? So the basic idea is that if we want to be able to use these larger resources, we have to get different things to work together. And that's what we're talking about here now. So you don't need to know everything that I'm going to say now. So it's an intro. The purpose is so that way when you come to another course and start reading a little bit more, it will start to make sense and you can sort of piece it together already. I'm not telling you enough to know how to actually do things. So let's talk about some jargon. So in this metaphor, a single burner is a CPU core. It's a thing that can do calculations. A cook is something that is following the code. It's a process and doing cooking. In the metaphor, a cook can only manage 1 pot at a time. Okay. The counter space is memory, and that's sort of the working area of processes. And there's one more thing that's a bit hard to explain within the metaphor. So that is threads. So the process is a fundamental unit of requesting resources, and a thread is the fundamental unit of doing computing using a certain burner. Yeah, there's something interested in the camera. Okay, where was I? So a process can be divided into multiple threads, and the thread is the fundamental unit of something that can use the burner. And I don't know how to explain this in the kitchen metaphor. My best example is that it is like a shadow of me. So it has to stay close to me as part of the same process. It can't go to another kitchen, another server. It uses all the same resources as I have, but can be doing something else, can actually be watching a different pot. So let's begin. What are the different styles of doing computing work, or splitting this work up? So first is embarrassingly parallel. And we call it embarrassingly parallel because it's almost embarrassing how easy it was to get stuff to run in parallel. And the simple answer here is that your code isn't parallel. You take the same code, the same recipe, you give it to a bunch of different people, and they all follow it separately, and they all put the results somewhere. So you might get a bunch of people here that cook the same thing or slightly different things, and then put all the results in the fridge, and we come back later and it's all there. An example here might be like a potluck or something like that, or a picnic, where a bunch of people make their own food and they bring it. So the advantages here is it's really easy to run, but it's sort of limited in how much resources it can use. But it can be combined with the other strategies I'm showing here. So if you want these jobs, embarrassingly parallel jobs, to do something slightly different, we have array jobs. So the array is part of the scheduling manager, and it basically takes one single job, like one single set of instructions, and you tell it run this 10 or 100 or 1,000 times, each with one different parameter. So it gives it one different number to the inside. And that is used somehow in the recipe to do something different. It might scan a parameter space or might run with different input data. In this metaphor, an array job, we'd have the same recipe, but it says if you are number 1, then use this ingredient. If you're number 2, use this ingredient, and so on. So we get slightly different pastas out. It's basically the same, but a different core topping on top of it. So the advantage of array jobs is it's easy. It lets you scan parameter spaces or run slightly different things really well. And yeah, it's a very well and often used thing. Next up is shared memory. And a common framework that does this is OpenMP. So in this, I have a process, and I have my shadows, and we're all working together. And the way we communicate is we have access to the same set of memory. So we have to be working inside of the same kitchen. And if we're working, then if I'm making something and I need to share it with someone else, I set it down on the counter where the other person is, or where the shadow is working, and they can pick it up and use it. So it's relatively easy to program, and allows you to scale up to the size of one computer node. Yeah, it's used inside of many different libraries. So since most computers have multiple processors, people want to take advantage of it. So this is, well, fairly often used inside of things, especially things like linear algebra libraries and so on. So for example, NumPy in Python and SciPy, they use this kind of parallelism to use multiple cores on a computer to do array operations. Okay, the next form of parallelism is message passing, often done with the framework called Message Passing Interface, or MPI. So this is what's often used for the biggest problems, because whenever you are passing messages, you can communicate outside of the kitchen you're in, or outside of the computer you're in. So in this case, you have different processes, so basically different cooks. They all have different counter spaces assigned to them. And in order to share anything, I have to pick it up and wait for the other process to be ready, and I hand something to it. And then it can take it into its own memory space and begin using it. So, yeah. This lets you scale beyond one node, and it's what's used for the tens of thousands, hundreds of thousands of processor core kind of physics problems or other things like that. Okay. One final thing we can mention is GPUs. So GPU doesn't fit this metaphor here. Well, it does, like the food truck I talked about before, the food truck that can cook 200 chickens at a time. So just be aware it's running a lot of stuff in parallel, but it has to be programmed specifically to use that. I'm just mentioning it here because someone might wonder about that. Okay, so what are some common problems? So one common problem is that people request resources. So for example, they request to run a job that needs 4 processor cores, and then they run a program that can only use one of them. It's not told how to use multiple of them, and that's wasting the resources. So for that, you always want to check your job and then make sure it's using things efficiently. So perhaps related, another common problem is someone thinks they can use a lot of resources, so they request a lot. Like, let's say they request 16 processor cores, and they go and they run their code on there, and they say, okay, well, it's not very efficient right now. They actually checked if it was being used well. And then they try a few things, but they give up and they say, well, my job isn't suitable for this kind of work. So it's good that they checked, but maybe it's not good they gave up so early. So what you should try doing is start small. Like, can it work on one CPU processor? And then can it run on 2 and 4 and so on? And slowly scale up. And by scaling up, you can see when it is that it starts becoming inefficient. And you can either stop there, or you can work to improve the speed, improve the efficiency from there. Another common problem, or not problem, but observation, is that making these encode parallelism things is hard. Not the hardest thing, but it's something that you really need to practice and get good at. Being able to make a recipe that can work in parallel. that knows how to use OpenMP or MPI. It really is its own thing that you can learn and get good at. There's all kinds of other problems that can come up there. So don't be afraid of doing it if you're interested, but realize that it will take some time. And that given how powerful computers are and that many codes are already slightly parallel, maybe using something like array jobs or using array jobs will get your problem done sooner and more efficiently than trying to make things parallel yourself. So with that being said, as almost every one of these videos ends with, you're no longer a cook that's cooking one thing on one burner. You are now the manager of all the cooks. You have to take the recipe, understand, can it be divided among multiple cooks? Can you decide what resources it uses? Can you make the batch job, the order, submit it, and then see the results when they come out? So, yes, hopefully this is interesting to you. And if not, well, it is something that you will probably start to see once you start using more and more parallel things and clusters in your work. So I hope that this has prepared you to come to our other courses where we do go into more detail about how to request these things. With that being said, thanks a lot and bye for now.